Well, we wanted to talk about modeling noise and individual variation. I'm going to switch gears a little bit from what you've heard so far and take a look at this a little bit from a translational perspective, how we apply some of these things. And if I can figure out how this thing works. The other way of coining this would be helpful noise. We've talked a lot about how noise can be looked at from various system perspective. Here we are going to look at a problem that somebody came to me with. And before I forget, I'd like to acknowledge a few folks. Jakob did most of the work on this, so I'm going to put his name out there right up there. This was a collaboration with Francisco's group at NIMH and Patrick. I'm going to be presenting a little bit of the work that Patrick did over there. All of this started because of Omar, who's a neurosurgeon at Brigham and Women's Hospital, and came to me and said, I have some data. I'd like you to build some models. And that's how we got started on this. And the other piece of this, we were able to put this data up on the Open Neuroimaging Laboratory, and that was a joint effort with a bunch of folks and one particular person. I'll point out as Roberto, who built BrainBox. Okay, so where did we start? This was the problem that Omar came to me with. I'm a neurosurgeon. I go and do surgery on people with meningioma. We need to be able to detect it. We need to be able to track it. We need to be able to predict the prognosis post-surgery. We need to be able to detect the difference in tumor or the resection volume, because that's what people do to determine the prognosis after surgery. And they do it by measuring lines on DICOM images. And being a person who would have gone and done a PhD in computer science had he not become a neurosurgeon, he said, I think we can do better. So at present, people do a surgery, look at the resection volume, and predict prognosis of the surgery. Obviously, he would like to bring this back, but a lot of this starts with a very simple problem, which is we need to detect things first. And we need to be able to detect things when they're not there, when they're there, and be able to look at the vast majority of scans going through these clinical institutions in seeing if that has a meningioma or not. Now, that's just one category of tumor. And I was excited because it's a simplest category of tumor. There are many more complicated categories of tumors out there. So this is what a meningioma looks like. And this is a case that's up on BrainBox. And I think even if you've never looked at a meningioma before, you can tell me what's different in that image because you've probably looked at a lot of brain images before, right? The nice thing about the platform, people can go there and label these things. So we have a segmentation or a labeled data set. And if people can do hot dog and no hot dog and actually come up with code for a TV show that runs, we figured we could do something like that. It also turns out that people can take images and label them extremely well these days. And there are lots of tools out there. So there are tools not only for general purpose deep learning, there are tools that are quite specifically targeted towards brain-based deep learning. So we said, we're in a good place. We have a problem, we can try to solve it. That's what we do. It also turns out that those brain-based tools, there are some nice networks that people have created. One is high-res 3D net, and the other is MeshNet. And these are pretty powerful network architectures. So I didn't even have to recreate anything. So that's always a good place to be, where you don't have to do anything and you can try to help solve a problem. Okay, so the first thing we said was, all right, let's build a framework to play around with this. We'll try to recognize a brain, and we'll try to recognize variants of this brain. And so we created what we call the no-brainer playground. It's a collaborative framework for defining, training, evaluating, and optimizing deep neural networks for brain images and processing. Our hope is to reduce time on complex operations. So even if we could do some of these things, it may help other people rather than just Omar with the meningioma problem. We wanted to create baseline models that understand brains. And I put understand in quotes because I'm not sure I understand brains, and I'm not sure our models understand brains either. But our hope is that. We wanted to implement models from literature. A lot of people are working on deep neural networks in various cases. And there's no reason for us to reinvent the wheel. We just wanted a framework within which we could implement these models and play around with it. So we built this architecture on TensorFlow. It trains with any NIBabble readable format with support for augmentation plugins. I'll talk about those in a second. And it runs on various HPC architectures with multi-GPU support. And one of the things for those of you who are familiar with or not familiar with neural networks is they take some time to train. They require a lot of data, and you require a fair bit of computation power. It's not the kind of thing that I can run on my laptop. Well, I could. It would just take me a long, long period of time. This is all open source, and it's under Jakub's repository. Okay. And then we ran into the first problem. So this is the meningioma dataset that Omar gave us. It has 35 brains. For that object or scene recognition thing that I showed you, it was trained with over 1 million images. Okay, how do I now train this network with 35 brains? And don't get me wrong, people have trained with smaller data set. It's just not necessarily going to be robust enough to all kinds of things. So luckily, we had a lot of other data. We had about 10K images that came from local data sets and the Abide dataset, which is a multi-site data set across ages for autism. And Abide 1 and 2 together, I think, are close to about 2,700 to 3,000 images. Our local data set spans 4 years to 65 years. So that's where we said, okay, variation can come in because we can look at brain sizes of different kinds. We looked at FreeSurfer outputs on all of this data. So we looked at the t1.mgz and the orig.mgz files, which correspond to an intensity normalized and a non-intensity normalized version of the same image. And we looked at APARC plus ASEG because we wanted to break it down to, can we understand what a brain is? And we looked at 2 different versions of this problem. One was, let's extract the brain. And 2 was, let's label pieces of the brain. And we created a bunch of training variants, and I'm very thankful to Dan for talking about some of these things. So we use various models, some with dropout, some with gradient noise, some with regularization. They allow for different kinds of noise exposure inside. We did various kinds of data augmentation. So we can't fit an entire brain into our GPU these days, although the latest GPUs might allow us to fit some of it. These things are quite memory intensive. And if you think of those deep neural networks with all those weights, they exceed the total number of weights, very quickly exceeds the total amount of memory achievable on a GPU. So we also optimized our framework so that we were able to fit in 128 cube versions of data into the brain and train with it at a given point in time. And that's a fairly large size by current standards, although some of the latest GPUs with 24 gigabytes of memory would likely be able to fit twice that size quite easily on the same network. And we trained for 30 hours on a single NVIDIA 1080 GPU. This was just to compare things across a variety of different models. We can actually run it across 4 to 6 to 8, as long as you can pack them all into a compute node in various ways. Okay, so this shows an example of the kinds of transformations we did to the same data. So the top left shows the original slice, and we're just showing a slice. We are doing this in 3D, but what we were able to do was to augment this in various ways. We changed contrast, we added speckled noise, we added Gaussian noise as inputs to the system. And lo and behold, it can look at a brain. So this is the output from the trained network. And when we validated this on an unseen data set, the dice coefficient, unseen but labeled, dice coefficient was about 0.97. And it takes about 30 seconds to run on a GPU. So that's pretty good. It takes about 3 minutes to run on a non-GPU. That's also pretty good. But that's a fairly simple problem. So we were excited about this at this point. Then we did the 50-class parcellation. And I'm not expecting you to detect all the problems, but this does pretty well for most part. And I'll show it to you with this, if it shows up. So what this is showing is it's going to fade in and out of the true label and the determined label by the network. And you will be able to spot a few differences here and there, but in general, it does a fairly decent job of detecting these labels. Then we sent this to one of those tumor data sets. And we were still quite excited at this point because look at it, it could figure out where the brain was and for most part left out the tumor. Then we gave it to another data set. And at this point, we said, huh, okay, we need to rethink how we are approaching this problem. So we haven't solved the tumor problem, really, because we haven't been able to train with all the variants that come across the various kinds of data sets that we have in terms of the kind of data that's collected at different hospitals. So that got us back to thinking about how do we think about variation in data? And a little bit later, I'll talk about how we can learn from multiple data sets that are out there. So first, variation in data. Brains come in all kinds of shapes and sizes. And we are quite familiar with it as the organization, Society for Human Brain Mapping. I don't know if the name is going to change, but it's a society now. But we are also able to deal with all these different kinds of data. And if I told any of you to detect the tumor in the middle image in the top row, you probably would be able to do that very easily because you have looked at images, you have a basic neural network that understands what a brain looks like and are able to pick things out. But if I asked you to do that in the bottom row, some of you may have some questions about where the tumor may or may not be. And the reason is that's post-surgery, and that doesn't quite look like the exact brain that we are normally used to seeing. So we said, okay, how do we learn from distributed data? And this is the work that was done by Patrick at NIMH using the no-brainer framework in looking at incremental and distributed learning. I was going to say that the next two slides are the only two slides with equations on them, but there is a third slide that comes up. I'm going to tell you not to pay attention. I'm just going to walk you through some of these equations. So the general idea behind any kind of learning system is you want to set the weights. And there are different ways of setting those weights on these neural networks. And a basic way of doing it is what's called a maximum a posteriori approximation, which is not good, but that's a way of doing it. Now, one of the things that has been created is this idea of variational continual learning, the idea that you can learn from data sets and continue the information from one data set to the next data set. And that's, again, I'm not going to go through the equation, but the general idea is that you can use prior information from previous data sets in training the next data set. What Patrick did was combine this idea to basically look at data sets being trained in parallel. So the difference in variational continual learning is that data sets are trained in series. In Patrick's work, in parallel weight consolidation, you can train data sets in parallel and aggregate that information. So again, I'm not going to go into the equations, happy to talk about it later on. But the general idea is now we have a mechanism by which we can send out models to different sites. They can train on their data, and we can consolidate the learning across those sites. And that's, I think, a powerful thing when you don't have access to all the data in the world, unlike the ImageNet data set, which is out there. Now, as people put more of these images out into the open, that'll be fantastic. So I'm all up for data sharing, but that might still take a while with respect to clinical and medical images. And this network does really, really well. These three things, B, N, and H corresponds to the Buckner dataset, the NKI Rockland dataset, and the Human Connectome Project dataset. These are single examples, and what we are looking at is the ground truth in the middle, and two approaches to doing this labeling. One, with parallel weight consolidation on the left. Two, with an ensemble method across the variational continual learning component on the right, and the leftmost and rightmost plots show areas where errors are occurring. In general, this system does really well, and I'm not going to have you look through all the numbers over there. I'll let you focus on the last column, which is A, right? A stands for a byte. This was a data set none of these models had seen before. And we were testing how well the models performed on that unseen data set. And if you look at the bottom right box, which are these ensemble models and these PWC models out there, you can see that on average, it does a much better job when you learn from these different data sets together as opposed to the individual data sets trained on. Okay, so I'm going to quickly go over the last bits of things. This brings us to something called the stability plasticity dilemma. The downside to sharing is overriding. In a highly distributed and massively interconnected system, how can the learning of one item not impact the learning of the second item when the synapses and nodes are shared? The system needs to be sufficiently plastic to rapidly accommodate new information without overriding old information. And if you thought that this was a solved problem, well, DARPA put out a call just last year, uh, which says these systems forget previously incorporated data. And in fact, if any of you have solved this problem, I would love to hear about it. Uh, MIT, which has a partnership with IBM, put out a call also last year saying, we haven't really solved this problem. We need to solve this problem. But some people have worked on solving this problem. So this is out of DeepMind that came out earlier this year, which says if we orthogonalize the changes into the space of something that's learning, where it doesn't influence what has been learned, that's one way of teaching a network new things without overriding the old things. But this problem has actually been looked at for almost 50 plus years in a computational sense. And I'm going to just take a raw poll over here. How many here have heard of adaptive resonance theory? One hand, two hands. Okay. So, oh, three hands. Adaptive resonance theory was created sometime around the late 70s, early 80s, right around the time when neural networks died a violent death. Because computers were slow, we couldn't do things. But it's really a way of looking at the problem from how a brain might implement a solution to the stability plasticity dilemma. And I'm not going to go into details over here, but the general idea is that it helps by creating mechanistic links between certain processes related to consciousness, attention, learning, expectation, and attention in a framework that's an unsupervised learning framework. Now, there have been extensions of it called ArtMap and others that extend it to a supervised learning framework. I'm not saying this is going to be a panacea for all problems, but it might be worthwhile for us to kind of go back and take a look at some of these things from that perspective. I'm going to skip this slide, and I'm going to go to this one. And this is one of the equations. I said there was one more slide with an equation, and I'm not going to ask you to look at the equation, but look at the plots. So what we're looking at in the plot is that there's an input pattern that the system is trying to learn, and there are different kinds of nonlinearities, and this links us back to deep neural networks in the system. And depending on the kind of nonlinearity that's applied to the input, we get different kinds of performance of the system. In one case, it can amplify the pattern or add noise. In another case, it can amplify noise without retaining the pattern. And then in the other cases, it creates sparsity in the system by restricting the information space to sparser representations of the input form. And that's kind of nice. If we go back to first principles or basic principles of how neural networks work, we might be able to think about ways in which we can re-architect neural networks. But this is a dynamical systems perspective. And right now, we haven't kind of figured out a way to combine the dynamical systems perspective with the current neural network perspective. So that's what we're working on these right now. So how do we need your help? We want you to make your data available, because the more data we have, we can approach this from different perspectives. We want you to make your models available. I'm sure there are many of you in the room who've developed different kinds of neural networks. Make them available so that other people can try out, because then they can help train models. We now have a framework thanks to Francisco and his group. And you can help test it out by providing errors on unseen data sets, which is, I think, the only way we are going to generalize to practical clinical applications. To summarize, neural networks can help speed up many image processing problems. Free surfer parcellation in 30 seconds is pretty good. Even if it's not great, that's still a fantastic engineering advantage. You could use that to detect a hippocampus very quickly on a scanner. We need to appreciate the variability in data to make generalizable and/or robust solutions. We often work on very small data sets and show the performance of our algorithms. The variation that exists in human brains for whatever specific aspect you're looking at is quite diverse. When I first started looking at the meningioma data set, I was like, I can track meningiomas. I can do the job of a radiologist. I soon figured out that no, there's a whole lot of variations that I'm just not exposed to. And if we want these systems to learn those things, we have to expose these systems to the kinds of variations that are seen. And finally, the dynamical systems may offer an alternative perspective on how to perform continual learning without catastrophic forgetting. That's something that's quite evident in the current proposals out there that ask for various projects in neural networks. And we have to be able to solve this problem if we want to have a realistic sense of how these trainable machines can help us in these clinical scenarios. Good. Thank you for your attention, and I think we're going to take some questions.